Hey now, everybody. Welcome to the next lecture. We're here in Remote Sensing Intro course, and today we're going to talk about digital photography slash UAS, which stands for Unmanned Aircraft Systems, otherwise known as drones. So it's kind of a two-parter. The reason I fit drones into this is, essentially drones are going to take digital photography, and the lab in particular that I have for you guys is, you know, uses drone images, and so we might as well lecture about it. There's certainly overlap between chapter 3 and 4 in terms of the photogrammetric concepts, so kind of keep that in mind. And with that being said, the flow should flow pretty well from what we learned last time to what we're learning now. We're just getting a little bit more in depth and then also exploring the UAS component with this. I will say the author doesn't provide any real any background, hardly at all, in the textbook in chapter 4. So just be prepared for that. There's really not, UAS is still a very new enterprise, and there's just not a lot of academic material available at this time. So just questions that related to drones, you'll know that it's, what I want you to get from it in terms of information is from this lecture and from these slides. And if you have other questions, because I know it's not in the text, please reach out, because it is a kind of a specialty niche of mine. So yeah, let's go ahead and start with all that being said. Just a little refresher, the film versus digital landscape. So the thing is that film photography was really the norm for many, many years, many decades, I would say, from really the whole 20th century up until the late or the early 2000s. And, you have something kind of standardized, but a new technology comes along, in this case, digital, and eventually it's going to get replaced. And so the last time I touched anything that was a digital photograph was in 2014. And at that time, I think I've said this before, but at that time, trying to find a vendor that sold film for aerial photography was a pretty tough task. So I'm not sure in terms of current landscape how prevalent or not film or film cameras are. Hence, everything is really moving into this digital, era. Advantages in this case, we have, well, I guess what we have noted here is the disadvantages of using film, right? And again, it's not to say that film is a bad thing, because it's actually very proven in terms of photogrammetric stereo collection. There's like a graininess to it. So I kind of think of it like, if you're an aficionado of vinyl and you really like the way records sound because there's just a different pureness to it, it's the same type of thing. It really is. When you talk to a photogrammetrist who's done stereo compilation for years and years, they'll probably swear by film because it's got this different, look and feel to it. At the end of the day, it's the same science, okay? And when we really break things down, film, you have to process it in a dark room with chemicals and space and time, etc. The storage of the film, the rolls of film, they're big things that you have to have space for. And you can't exactly just pop a roll of film into a computer and FTP site it or email it to somebody. Yeah, I mean, there's so much more involved with film as opposed to digital. So I know I might be stating some of the obvious things, but this is another reason why. And with drones, it's not even really a question. I don't know any drone that takes or that handles a film camera for that matter. But when traditional photogrammetry in large aircrafts, it's really the way things are going. Okay. So electronic imagery, digital imagery, right? When we say this, we're talking about digital sensors and recording information. So millions Okay, not just thousands, millions of pixels. And each one of those pixels is essentially picking up or scanning a unique part of the Earth as, sorry, I'm moving my screen over, that's why I'm looking over here. The Each one of those pixels picking up a unique portion of the Earth, right? A unique portion of the surface. Um, there's a sensor type called a charged coupled device, a CCD, and essentially what this thing does is it records the radiation, okay, electromagnetic radiation values onto a specific, like the sensor type is light sensitive materials, and it's all embedded on a silicon chip. The author goes into this stuff in greater detail, trust me. And so what happens is we end up with multiple rows and columns of digital arrays. Okay, so like stacked, boom, 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 boom. Like as if you're looking at a big table, right? Each one of those little cells, that's a pixel, right? And yeah, just looking at it from a microscope. So what happens is, okay, when we say linear array, we're talking about the array or the row of pixels like this in a linear line fashion. This is an example from a spot satellite sensor. Let's see, reported, each receptor within the CCD equates to 1 pixel within the image. So the reason I'm showing you this is kind of just a look at it behind the scene kind of thing. I'm not expecting you to necessarily understand all those little bits and pieces of it, but yeah, this is what a sensor is going to look like when you zoom in real close. And what we're seeing here is a difference in pixel size, 10 versus 100. This little mu sign, but this represents a micrometer in size. So 100 micrometers versus 10 micrometers. You know, this all relates to the pixel size, which we've talked about before, but we're going to get into a little bit more in this section. And pixels makes me bring up, you know, a very common terminology called megapixels. And let's understand what that really means, especially in the digital landscape. So megapixels, all right? When we say megapixel, we're talking about the image sensor and its linear arrays. So the image sensor has a fixed number of pixels in the X, let's call it the X, okay, in the horizontal, and a fixed number of pixels in the Y, in the vertical. So for example, sensor might have 4,000 columns. Okay, when we say columns, it's like boom, 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 but that would be this direction. Okay, so 4,000 by 3,000 rows this way, 4,000 by 3,000. And if we just simply multiply those two things together, 4,000 by 3,000, what do you get? Well, you get 12 million. 12 million pixels altogether in the entire sensor. What you end up with is a 12 megapixel, you know, rating of a sensor. So whenever you see that in a commercial camera, X amount of megapixels, that's what they're talking about, okay? The X amount of pixels times the Y amount of pixels. That's all that it is. But yeah, it's in the millions of pixels range. In the early 2000s, when digital photography was coming along, you know, you'd get something in the realm of, you know, if you had a 1 megapixel rating with you know, meaning you had 1 million pixels, it was phenomenal. But I would say, I mean, on a phone, you're looking at, gosh, I don't even know what the latest iPhone's got, but at least 12, like in this example, and sometimes upwards of 20, 24, even more than that. Drone cameras have megapixels have expanded exponentially over the last couple years, to the point where we were first talking about a few megapixels ratings to now in 2021, there is a camera on the market that has 45 megapixel rating, which is a phenomenal achievement. Okay. Just to give you another little tidbit of information that's not part of the book, the cameras that you find on a large aircraft, digital cameras that you find on a large aircraft, I don't think I have any examples, but so for example, I'll tell you a name here. There's a company called Vexel. VEXCEL. And they make a large frame. Okay, when I say large frame, like think of this entire box filled up. But I mean, huge. You're talking a 300 megapixel rated camera. All right. But again, this is for large aircraft, thousands of feet in the air, trying to map, you know, big areas of surface at a time. And that's kind of what it's involved there. Yeah, here's another little tip for you. When you are trying to figure out, you know, how many megapixels is my camera? I don't know. It's just a picture. Well, you could figure that stuff out by going into the properties of the image. And for example, if you go to the details pane tab, you'll find the width and the height. So the width is the X, the height is the Y. And just take those two things, times those together, and there you go. There's your megapixel rating. This is just some random one I found of some random picture I found that I'm using for an example. Focal length. There's a ton of different digital camera, like your aperture and your shutter speed. I mean, you see them right there. If your camera has a GPS, or the drone's camera has GPS, it will also embed the latitude, longitude, altitude into this metadata. There's your focal length, right? And we learned about focal length and how important that is, because focal length determines, or is, you know, kind of one of the parts of the formula for determining how high or what kind of sample distance is going to be resolved, right? And you can find that right there in this example of 3mm. This is probably some person's phone camera. I'm not sure. Okay, and so yeah, sensor size and megapixels, there is a relationship between the two, but they're not necessarily the same thing. And I want to make note of that, because it's important. Now, the thing is, with megapixels, we could talk about millions and millions of pixels and how great it sounds. But the fact of the matter is, higher megapixels don't necessarily mean higher quality imagery. So the reason being, if you have a very small sensor, like I have one of the smallest phones on Earth, and everybody tells me that. So I know this is retro 10 years ago, but I love it for the size. In fact, what I'm trying to get to here, look at how small this camera is. Even if this camera is a 12 megapixel rating, it could be, it could have the same megapixel rating as like this point and shoot camera, right? Look at the difference between these two things. Now, the sensors on these two is going to be quite different, where this one is going to have a very small physical size sensor. This one's going to have a much larger in comparison. But for all intents and purposes, they actually do have the same megapixel. Yeah, this one's 12 megapixels. They do have the same megapixel output. The difference between the two, with this being a larger sensor size, the image quality is going to be much better, because what happens is, with imagery, you're talking about, and with photography, right? These are kind of photography basics now. You're talking about how light is registered with this sensor that we, this light, the thing we talked about a few slides ago. Anyways, what I'm trying to say is that the more light that can essentially be registered or not, the better the output is going to be. I mean, physically, it's going to look like a cleaner, crisper output. So when you have a larger frame, you end up having larger pixel sizes, even if the megapixel is the same. You can have the smallest camera ever and have a high megapixels. It just means that the individual pixel sizes on that camera are very small, meaning that they do not have a very high dynamic range. Dynamic meaning that there's a wide spectrum, right, of how much light can be ingested there. So this is what I'm trying to get to. And, essentially, if it's one versus the other, a larger sensor is going to be a better, larger sensor versus higher megapixel. A larger sensor is going to yield better results compared to a smaller sensor with the same or even higher megapixels. Now, if you can get both, I mean, great, right? That's the idea. So that's the conclusion. Larger sensors always going to be better. This is kind of giving an overview of what your 12 megapixel, generally what your 12 megapixel sensors on like a phone will look like, something like this size, okay? And just think about the surface area that you have to cover with something like this, even compared to a 1-inch sensor, or over here, 36 by 24, which was considered full frame. Now, if you have a full frame, you're talking big DSLR, professional photography. You know, there's a reason that thing is so heavy, because the sensor inside is so big and heavy, okay? Let's move on. Okay, pixels. There's a lot of talk about this. So pixels, let's break this down. Pixels means, when you say pixel, it means picture element. Pixel, that's a pixel. A pixel, a minute area of illumination on a display screen, of many from which the image is composed. Wow. So basically what we're saying is, we've already kind of described this, right? So it's a part of the, now, so we know that the sensor has these pixels, how they're broken down into these linear arrays, and how that's broken down as we saw earlier. The pixel is the correlation between that versus when it turns into an actual image, okay? So as we zoom in on an image, every one of those little squares, that's a pixel. That's a pixel. Let's bring all these out here. So the smallest area that can be separated or recorded as an entity on an image, right? So that's what I mean. When you zoom in and you can see that little tiny square, that's a pixel. So that's the smallest thing that can be resolved. And pixels possess something called, and we could say this in either way, a digital number slash brightness value, BV, okay? Does the same thing, right? And I'll get more into those as we go through this. But just remember that right now, that every pixel that shows up in an image has a digital number or slash BV associated with it. Now, pixel spacing, i.e. size, okay, it's going to vary with the sensor. And we learned this before, okay? The sensor X here, okay, times how many, or divided by how many X numbers exist. So what we're saying is how many columns exist. That, okay, so how big is the physical size, like what this one was? Like if we use one of these examples, the first example there, if it was 1 inch, we're talking 12.8 times, or divided by the number. So maybe by 4,000, and that would give us, boom, pixel size. Okay, pixel size. Which all comes back to what were we talking about? All these things. Yeah, I'm not going to repeat myself here. Okay, so we learned this a little bit, ground sampling distance already, and then it's going to come up a lot more, especially in this lab. GSD, we call that, that's a frequent way to call it, GSD. Now the author is going to refer to this as a ground resolve distance, and that's fine, GRD. It's the same thing. The GSD, it pertains to the size, the smallest feature that can be resolved. Essentially, what we're talking about with GSD is the GSD is the relationship between what's in the actual scene and the photographed. So like, for example, whatever the features are and how resolved those features are. And in particular, the size. So like if I had my screen and I was measuring the little square, if I zoomed in all the way and I measured the square on one side and it said, you know, I'm using GIS and it said, this thing is 1 inch by, 1 inch across. So as I zoom out, I go, oh, that 1 inch represents a trash can. So what it's trying to say is your GSD is a 1 inch, okay? And another way to refer to this would be a pixel size. There's a lot of pixel and sampling and distance and all. A lot of it can get intermingled, all right? I'm trying to do my best to separate these things, and you really want to compartmentalize the differences, even though there's a lot of repeated terminology and they kind of mix together. Your pixel size, it's different than, well, pixel spacing. Maybe we shouldn't use these things in the same way or the same. Let me just make a point here. This slide, when it says pixel size, is referring to, I'm gonna actually remove this, is because this is just confusing. There you go. Okay, all in one take. So this pixel spacing is different than your pixel size in this context. Okay, when I say pixel size here, oh geez, we have it again. Boy, I should really review these ahead of time. I guess I know I do, right? But sometimes things get slipped past there. Anyways, let's just refer to pixel size and call that ground sampling distance. Same difference, okay? Now, pixel size, as it's being, your pixel size is one of the final, like if let's say we're processing imagery and we're processing a mosaic of imagery, in particular like an orthomosaic, which you're gonna do in the lab. Your pixel size is one of the things that you can actually manually set. Now there's a kind of averaged out version of what that's going to be based on what the computer's photogrammetry spit back out at you. But say, for example, you wanted to resample that, and instead of it being, let's say, ×1 or a 1 by 1, you could make it a 2 by 2 or a 5 by 5 or something like that, okay? There's another example of subsampling it to a smaller number size, but I don't recommend doing that. I really don't, because you're not actually resolving anything more by doing so. It's just adding disadvantages, in my opinion. Let's move on. Okay, we've seen these kind of things already. Here's your pixel size / spatial resolution / GSD, all here in one place. So let's say you have a 30 meter. Now what we're looking at here is the reality and the pixel size here versus what's actually there, and then how that will correlate in the raster. And in this case, if it's 30 by 30 and the blue house is like the majority of what's in the pixel, well, then the pixel is going to be just kind of a big blue blob. All right. Now, if we had something that was much finer, down to 6 times less, 5 meters in size, what you have is something like this. And then if we took it even further, 5 times smaller, down to 1 meter, you're going to get a pretty good representation. So the moral of the story is the finer the pixel size, i.e. the smaller this number is, the more resolution you're going to resolve. Okay, the better the resolution, the better the picture is going to resolve, the higher the resolution is going to be. All right. Let's move on and talk about something a little bit different now. Some of this is review. I mean, I know that we've covered these topics briefly, but it's all supposed to come full circle here. So spectral sensitivity, this is referring to the, there were the 4 types in the beginning, right? Spectral, radiometry, temporal, etc., right? Types of resolution, and spatial. Now, this is in relation to spectral resolution. And so what we're talking about is, we talked about this before, the band window. I think that's what I referred to it as. Where is what band or what channel is the specific spectral resolution or sensitive? Where is it sensitive to that particular spectral range on the spectral radiometric spectrum? So, okay, minimum and maximum wavelengths at 1/2 of its potential maximum value. Let me just show you over here, because this is a better way. I guess I like pictures more. I don't know. But the best way to decide or define what the best spectral resolution is going to be for a sensor is we evaluate along the radiometric spectrum, where is that wave, okay? Like in down here, and could be nanometers, could be, whoops, let me go back.